Hello, and welcome back to Physics 141, Classical Electromagnetism 1. So for this lesson, we need to review the concepts of a dipole as what we have presented during the lesson on multipole expansion. So if you will recall, the potential of a pure dipole, sometimes also referred to as a point dipole, is given by this. So 1/4 pi epsilon naught, then r hat dot p, or this is just a dot product, it can also be written as p dot r hat over r squared. Or again, the curly r here is the separation distance from the dipole, and p is your dipole moment. So for this lesson, we will be talking about polarization in dielectrics. So we have presented in the previous lessons that when an electric field passes through a material, the material has an induced dipole moment, and hence the material becomes polarized. So in this lesson, we will first start by relating the relationship between polarization and dipole moment. So polarization is essentially dipole moment per unit volume. So you're just describing the amount of dipole moment per unit volume of the material. So essentially dipole moment and polarization are the same. So in terms of in an equation, we can write it as dp d tau, where tau here is the volume. The dipole moment per unit volume. It could be the total dipole moment over the total volume. So what happens now when an electric field passes through a material? So we will be presenting two cases for insulators or dielectrics. The first one is if your material or your material or dielectric is made of nonpolar molecules. When you say nonpolar molecules, these are molecules which don't have an inherent, or which don't have their own dipole moment. So unlike water is a polar molecule. One of its side, the oxygen side, is negative, the hydrogen sides are positive. So it has a dipole moment. So these molecules are nonpolar. They don't have a dipole moment. Now, when you expose it to an external electric field, what will happen is there will be induced dipoles or induced dipole moments in each of the molecules. So making the molecules essentially polar. So from nonpolar, they become polar molecules. So if you have polar molecules at the start, if your dielectrics are made, a dielectric or your insulator are composed of polar molecules, then that means that they already have their own individual dipole moments for each of the molecules. And if you expose that to an external electric field, as we have discussed in the previous lessons, it will exert a net torque on the dipole, making the dipole rotate. So essentially, the dipole moments of these polar molecules will just align with the net external field. And as you can see, the final result of a dielectric, whether it's composed of nonpolar or polar molecules, are just essentially the same. They have dipole moments which are aligned with the field. So in both cases, we say that the material is polarized. So polarization is essentially having dipole moments aligned or within the material, which is aligned to the net external field. So the question now is, what is the field of a polarized object? So we can actually do this by integrating the electric field of every dipole here. Since we already know the potential of a dipole, then the negative gradient of that is the electric field of a dipole. So the field of a polarized object can actually be obtained by integrating all the fields due to the individual dipoles. So from our the equation of a pure field potential of a pure dipole, the differential potential will be given by this, and integrating this will give us this equation. So this is now the potential of a polarized object in terms of the polarization P, capital P. Again, P here is now dP over d tau, differential volume. We can actually also translate this equation using some vector properties such as divergence theorem, and we can transform this integral into this. So this is now also the field of a polarized object, but now it's in terms of what we call bound charges. So sigma b is what we call the surface bound charge density, and rho b is the volume bound charge density. So the surface bound charge density is just essentially the polarization, that with the n hat. N hat again is the normal unit vector, the unit vector perpendicular to the surface. However, the volume bound charge density, rho b, is just the divergence of the polarization. So if the polarization is diverging, spreading out, then you have bound charges. So when a material, a dielectric for that matter, has a polarization now due to any say an external electric field, for instance. So if a field or a material is now polarized, if a dielectric is now polarized, it can have volume bound charges, so bound charges within the volume, or it can also have surface bound charges. So in general, it can have both, but in some cases it can only have volume bound charges, but it can only have surface bound charges. But in general, it can have both bound charges. So take note, these charges are from the word bound, meaning they cannot move. Unlike the, say, electrons in a conductor, those are free charges. So essentially they can move from one atom to another. But take note, these are bound charges. These charges are actually just stationary. For example, if you have surface bound charges, then you have, say, positive charges here, positive charges here, positive charges there, and those are bound. They cannot move within the volume or within the surface of your material. Okay. So let's have an example about polarization. So here we have a non-uniformly polarized sphere. So this is our sphere of radius r. So it's a sphere of dielectric material. So this is an insulator, a sphere of an insulator. It can be a sphere of a plastic or a sphere of glass. And its radius is r, and it's polarized. Polarization is k times r. So meaning, what does this mean? Your polarization is this is just the position vector r, and in spherical coordinates, the position vector is just r times r hat. So that is basically your polarization. So what does this further means? This means that the polarization is only along the r hat direction, the radial direction. So this means that the polarization actually radial. So this is the polarization. The polarization is radial. Okay. And it's non-uniform. It depends on the value of r. K here is just a constant. So depending on the value of r, your polarization is different. So the polarization, as you go near the surface of this sphere, at R is equal to capital R, that's actually the maximum or the highest polarization. So there's actually zero polarization at the center, and the polarization increases as you go from 0 to capital R, from the center to the surface. So we are asked to find the surface and volume bound charge densities first, and then find the electric field everywhere, and calculate the potential directly using the given polarization. Okay, so that's it. So let's first start with letter A. Find the surface and volume charge densities. Okay. So take note, the polarization is essentially the dipole moment. And the dipole moment always points from the negative to the positive charges. So what does this mean? This means that there's negative charges somewhere at the center, and there will be positive charges at the surface. So this is what the charge distribution of this polarized sphere looks like. So by the way, these are bound charges. So these charges cannot move. They are bound in the surface. They are bound within the volume. Okay. So for letter A, find the surface and volume bound charge densities. So the surface bound charge density is just the polarization that with the unit vector n hat, the unit vector normal to the surface. In this case, n hat, if this is, since this we only have one surface, R is equal to capital R, so this is n hat, the unit vector normal to the surface, and that unit vector is actually the r hat direction. So basically, we need to solve for the bound charge density. We need to evaluate this at the surface or at the boundary at R is equal to capital R. So we have the polarization. It's K R hat. You dot it with R hat, and then you evaluate the result at R is equal to capital R. So you will get R hat at R hat, that's just 1, and you will get K times capital R. So this is the amount of bound surface charge densities at the surface. And you will notice that it's positive, so there are positive charges at the surface. How about the second question? Volume bound charge density. So to solve for the volume bound charge density, we get the negative divergence of our polarization. So since this is our P is only composed of the R component, then in the divergence formula in spherical coordinates, we will just use the R part or the R terms or the R term. So this is just equal to negative 1 over R squared partial with respect to R of R squared and the R component, which is just K times R. So our polarization is only has an R component. It doesn't have a theta or a phi component. So you have KR, so this R cubed essentially. So this will give you a value of negative 3K. So you will notice the surface bound charges are positive. The density is K times R. But within the volume bound charge density is actually negative 3K. It's actually constant. So a more accurate representation of this is that within the volume of the sphere, there are negative charges within the volume, but on the surface, there are only positive charges. So that's how you interpret this result. So it's negative, meaning negative charges, and it's constant. It doesn't depend on R. So meaning that it's uniform charge distribution within the volume. Okay, so basically that is for letter A. Let's now go for letter B. Find the electric field everywhere. So to find the electric field everywhere, the question meant find the electric field inside and outside the sphere. So for the electric field inside, we can actually just use Gauss law. We can have a Gaussian surface here, the radius r, and then calculate the charge enclosed. So since the charges enclosed by our Gaussian surface are negative charges, then that means that the electric field inside must be inwards. So the electric field inside must be towards the center of the sphere. Okay, so if you use Gauss law in this manner, so you will have the closed integral of electric field inside dot dA, our a small errors, equal to the charge enclosed over epsilon naught. Okay, so E dot dA, this will give you essentially the electric field inside is towards the center. dA in this case is outward, it's perpendicular to the Gaussian surface, so this will be negative electric field inside times the area, which is just 4/3 4 pi r squared rather. And the charge enclosed, basically since there's a uniform charge distribution, it's just the volume charge density times the volume of our Gaussian surface. In this case, this will just give us, we have solved this, it's negative 3k, and the volume is 4/3 pi r cubed. So the charge enclosed will just give us negative 4 pi r cubed k. Okay, cancel ang 4 pi r squared, negative and negative sign. So the magnitude of our electric field inside is k. Sorry, there's an epsilon naught here. So k over epsilon naught. So this is the magnitude. If you want to convert this into a vector, then the direction of this is negative. Sorry, there should be an r. Sorry. So since r cubed divided by r squared. So the direction of this is negative r hat because it's towards the center. It's basically the field of a negative charge. So this is now the electric field inside. Okay, we can do the same for the electric field outside. So we use Gauss law, we make a Gaussian surface outside, then find the key for Gauss law is finding the total the charge enclosed. So this is now the electric field inside. For the electric field outside, we will achieve with the same solution except for the charge enclosed. So what's now the charge enclosed if we are trying to find the electric field outside? So the charge enclosed now, if your Gaussian surface is now outside, it will now be due to the surface bound charges and due to the volume bound charges. So you have sigma b dA plus rho b dV. Okay, so this two are just essentially constant. The bound charge densities are just constant. We have obtained them before. So the surface charge density is just Kr, meaning the integral of dA is just 4 pi r squared. This is also constant. It's negative 3K, meaning the integral of dV will just be the total volume of the sphere, 4/3 pi r cubed. So you will have 4 pi k r cubed. And this one cancel ang 3, 4 pi k, negative 4k pi r cubed. So your charge enclosed will now be 0, meaning your electric field outside will also be 0 since there's no charge enclosed. So essentially, if you have a polarized object like this, the bound charges will distribute themselves in such a way that the whole polarized material is still essentially neutral. So the total charge is still 0. So this is what you have when you this is what you get when you have a frozen in polarization, a polarization that is already frozen within the material. Essentially, there's no electric field outside of the material, only inside of the material. Okay. For the next problem, so we need to use the given polarization directly to solve for the electric potential everywhere. So from our equation that we have obtained, the potential is just 1 over 4 pi epsilon naught integral of r dot p over r squared dV, or the differential volume for that matter. Okay, I am just gonna use the board mode here. We'll have a long solution. So this is our starting equation. In this case, because of symmetry, and our origin is at the center of the sphere, we can just let our curly r hat, the separation distance, as the r hat vector. So in this manner, we'll have 1 over 4 pi epsilon naught r hat, that our polarization is kr r hat over r squared. The differential volume is just r squared sine theta d theta d phi dr. Now, if you will notice, inside the integral there is no theta or phi, meaning the integral on phi and theta will just amount to 4 pi. So instead of this, we can also write this as 4 pi r squared dr. So the integral of sine theta d theta, integral of d phi will contribute to, or will become 4 pi. Okay, so r hat, that will give you 1. There's an r squared here, there's an r squared, there's an 1r. So what's left inside the integral will be r dr. So cancel ang 4 pi, and I will have k over epsilon naught integral of r dr, and I will evaluate this from 0 to r, since we are evaluating inside the potential. This we are working now for the potential inside the sphere. So this is just r squared over 2, and you will get k r squared over 2 epsilon naught. So this is now the potential inside. So how about the potential outside? So if you use the same formula, there is no polarization outside of the sphere, meaning you can't use essentially this equation. So what does that mean? If we go back to our figure, what does that mean when earlier we have found out that the electric field outside is actually 0. So the electric field outside is actually 0, which means that the potential outside must be a constant. So that is what this means, because the electric field is just the negative gradient of the potential. If the potential is constant, then the gradient of the potential is 0. So the potential outside is constant, which means whatever is the potential at the surface of the sphere, that is the potential outside of the sphere. And based from the potential inside, since the potential is continuous at the surface or at the boundary, the boundary here is at r is equal to r. So at r is equal to r, the potential inside must be equal to the potential outside. And when r is equal to capital R, that will just give you k capital R squared over 2 epsilon naught. Essentially, this is the potential outside. It's constant, no matter how far the field point is from the sphere. You can also verify, by the way, the electric field that we have calculated earlier. You can take the gradient of this, negative gradient of this, and you will obtain the electric field inside, the one that we have obtained earlier. Okay. So to summarize, for letter A, these are our results for the bound charges. For letter B, these are our results for the electric field inside. So we just we actually wrote it in terms of k r hat, but r hat is just the r vector, and basically k times the r vector is our p, our given p. So we can actually write the electric field inside as negative p over epsilon naught. So essentially, the electric field is just proportional directly to the polarization. For the electric field outside, we found out that it's 0. And for the potential inside, we found this value. Again, if you take the negative gradient of this, you will get this result. And for the potential outside, it's constant. K capital R squared over 2 epsilon naught. Okay, let's now go to the second example for this lesson. So for this example, we have a uniformly polarized sphere of radius r. So the polarization is uniform. This means that inside the sphere, unlike the previous example wherein the polarization is radial, the polarization inside the sphere here is actually uniform. So these are the direction of the polarization inside the sphere. Okay. So you are then asked to find the electric potential and the field of a uniformly polarized sphere of radius r. Okay. So how do we do this? So in order to solve this, we need the general solution for finding the potential in spherical coordinates. So I'm just gonna go to my board mode here, and I will try to draw again the problem. So we have a sphere of radius r and uniform polarization P. Okay. Are there bound charges here? So we can actually solve for the bound charges at the surface bound charge density. It's just P dot n hat evaluated at the boundary or the surface, r is equal to capital R. So in this case, so we will assume that this is the z direction. Sorry. This is the z direction. So this is the r hat direction. So the r hat actually is our n hat direction. So in between the z axis, which is the direction of our polarization, so we can actually let our p vector as having a magnitude p and a direction of z hat. So that one. So p dot n hat, where n hat is our r hat, that will give us what? So the angle between the z-axis and the r-axis is actually theta. So theta, the polar angle, is actually measured from the z-axis and then to the negative z-axis. So basically, we will have is just p, then z hat, that with r hat. And if you use the general, if you just use the general definition of the dot product between two vectors is just the magnitude of the first vector, which is p, and the magnitude of the second vector, which is a unit vector, which is 1, cosine the angle between them. So this is actually the surface bound charge density, p cosine theta. It depends on the angle between your r vector and your z-axis theta. Okay, so what does this bound charge density mean? So when theta is equal to 0, cosine 0 is 1. You have the maximum bound charge density. And when theta is equal to 90 degrees, meaning cosine of 90 degrees is 0. So if I'm going to draw again the sphere like this, at theta is equal to 0, there will be a group of positive charges here. Surface bound charges rather. And there will no longer be any surface charges when theta is equal to 90 degrees. So this is the 90 degree location. And when theta is equal to pi, 180 degrees, it's negative 1. So negative p, meaning there will be negative charges here, concentrated at the south pole. So this is the picture of this surface bound charge density. There will be positive charges on the upper region, and there will be negative charges on the lower region. There will be no charges in the equator of the sphere. Okay, so you will notice that it will have an electric field which is directed downwards. So this is the electric field inside. Actually downward because it's from the positive to the negative charge, and the polarization is reversed. The polarization is actually upward. So we will expect that our electric field inside will be in the direction of negative z hat. Okay, how about volume charges? It's the negative divergence of p. But since p here is a constant vector, it doesn't depend on r, theta, or phi, then it has no divergence. So you can also see that it has no divergence because it's only in one direction. It's not spreading out. So there's no divergence, zero divergence, meaning there's no volume bound charges within the sphere, only surface bound charges. And this is actually what happens if you have a uniform polarization. A constant polarization means there are no bound charges. So no bound charges in volume. Only surface, only on the surface. Okay, so in order to solve this problem, we actually need just this one, the bound charge density. So in order to solve this one, we need to treat it as a boundary valued problem. So for instance, if we want to find the electric field inside, so inside the sphere, we have this boundary condition. So as r approaches 0, the potential must be finite. It must not be infinite. And at r is equal to r, the potential inside must be equal to the potential outside. Okay, we will not call this the inside boundary condition, or just the generic na lang na boundary condition. So as r approaches infinity, the potential must approach to 0. Since there's no electric field outside, the potential outside as r approaches infinity must be equal to 0. And at the boundary, at r is equal to r, there will be a discontinuity in the electric field or in the derivative of the potential. So the derivative of the potential outside with respect to r minus the derivative of the potential inside with respect to r must be equal to the negative surface charge density, which is this one, over epsilon naught. So these are the four boundary conditions that we need. And we will, your solution should start with a general solution for spherical coordinates using separation of variables. So it's in terms of Legendre polynomials. Okay, so from this, if we apply boundary condition 1, we can actually formulate the general solution for the potential inside. So for the potential inside, if we apply boundary condition 1, as r approaches 0, the potential must not be infinite, or must be finite. So this term, r to the negative L plus 1, when r approaches 0, this will actually reach infinity. So we must set dl to be equal to 0. So therefore, inside, this is your general solution for the potential inside. For the potential outside, we apply boundary condition 3 to this equation again. So when r approaches infinity, this term actually approaches to infinity, meaning we need to set our ALs to be equal to 0. So therefore, there's no ALs, only pure BLs for the potential outside. Okay, so this will now be our starting points. So we need to apply boundary condition 3 at r is equal to capital R. So equate these two. It should be equal at r is equal to capital R. Okay, I'm gonna solve just applying the boundary condition 2, and I will leave the rest to you. Okay. Can I use another board? Okay. So at r is equal to r, using boundary condition 3, so the potential inside at r is equal to r must be equal to the potential outside at r is equal to capital R. So potential inside, this one, summation of L, AL, R to the L. It's now r is equal to r, capital R, PL of cosine theta, equal to the potential outside, BL, R is equal to capital R, to the negative L plus 1, PL of cosine theta. Okay, so we use something like a Fourier trick here, wherein we multiply both sides by PL prime and then integrate over the differential of cosine theta. So what we will do here, we will multiply both sides by PL prime of cosine theta. I'm now gonna neglect the as a function of cosine theta na notation para dili, so that our equation will not be that long. So and then, so I'm just gonna highlight what I'm gonna put it in a different color. So we multiply both sides by PL prime of cosine theta and then integrate over cosine theta from negative 1 to 1. So that is what we did. Multiply both sides by PL prime, then integrate over the cosine theta. We'll also do that on the other side. So r to the negative L plus 1, you have PL, and I'm going to multiply PL prime and then integrate over the differential of cosine theta from negative 1 to 1. Okay, so this is the what do you call this? A property of the Legendre polynomials, and this is just equal to 2 over 2L plus 1 delta L L prime. Similar with that one. That's also 2 over 2L plus 1 delta L L prime. So what will happen here? If you because of this delta function here, you are forced to take only the value of L in the summation here, which is equal to L prime. Because if L is not equal to L prime, this is equal to 0. So only one term in the summation will survive. The term L is equal to L prime. So only one term now will survive. So you have AL, R to the L. There's 2 over 2L plus 1 here. There's 2 over 2L plus 1. So the 2 over 2L plus 1 will just cancel each other out. And then you will have BL R to the negative L plus 1. Okay. So from here, we see that BL can just be written in terms of AL. So AL R to the 2L plus 1. So meaning, I can just replace BL here. I can just replace this by AL R to the 2L plus 1. And my only unknown now is AL. So you can find AL by using the last boundary condition. So you need now to take the derivative of these two with respect to R, evaluate it. I forgot to put the evaluation. You must evaluate it at R is equal to capital R, and then equate it to the bound charge density, which is this one. So the key here is you still need to use the property of Legendre polynomials. So you can actually write cosine theta as P1 of cosine theta. That's actually P1. Cosine theta is actually P1. P0 is 1. So P1 of cosine theta is actually cosine theta. So you can actually use the Legendre polynomial here. P times P1. So this becomes P times P1. So you still do the same. You multiply both sides by PL prime. So you will notice that you already have a P1 here. You multiply by PL prime. So you will have something like a delta 1 L prime. So because of that, L must be equal to L prime, and it must be equal to 1. So only one term in these summations here, only one term will survive. L is equal to 1. The rest of all the ALs are 0 because of this boundary condition. So you will notice that only one term, A1, and you can solve for A1 actually. So you do that. I will leave that to you. And basically, what will happen is you will only have one term in the summation for the potential inside. It's just A1 R to the power of 1 P1 of cosine theta. And this will actually give you can actually solve for A1. And this will give you PR cosine theta over 3 epsilon naught. For the potential outside, also one term. So you have A1 R to the 2 R cubed R to the negative 2 P1 of cosine theta. And this will give you P, the magnitude of the polarization, R cubed cosine theta over 3 epsilon naught R squared. So this is now your potential inside and potential outside. Now, what we are asked in the problem is actually the potential, the electric field everywhere. The electric field inside and the electric field outside. So to find the electric field inside, you take the gradient of the potential inside, so negative gradient of the potential inside, and this is actually just the negative, if you will notice, our potentials are functions of r and theta. So it means we need to get the del operator for r and theta. So this is actually partial with respect to r hat, plus 1 over r, partial with respect to theta hat. So we'll no longer include the phi component since there's no phi here. And we will apply this operator on the potential inside, which is p r cosine theta over 3 epsilon naught. Okay, what do we get? So for the first operator, with respect to r, so you will have negative p. I'm just gonna take out all of the constant, no? So you have constant p over 3 epsilon naught. And then the derivative of r, cosine theta with respect to r, is just essentially cosine theta, r hat. So there's an r hat. Plus the derivative of r cosine theta with respect to theta multiplied by 1 over r. So if you multiply that by 1 over r times r cancels out. And the derivative of cosine theta is negative sine theta. So this is our electric field. But we can actually further simplify this. If you will notice, if this is the z-axis, an angle theta from the axis, the z-axis, that's actually your r hat. So this is z hat. And an angle theta from z hat, that's actually your r hat. And an angle of 90 degrees from r hat, that's actually your theta hat. So this is 90 degrees. So we can actually write the z hat unit vector in terms of the r and theta coordinate system. So if you just rotate that, you will notice that z will have a cosine theta component in the r hat, and will have a negative sine theta component in the theta hat region. And essentially what I'm saying is that this vector representation here is just your z hat. So as we have predicted earlier, the electric field inside is actually directed along opposite the direction of the polarization, negative z hat. So actually I can also write this as negative p over 3 epsilon naught, since the polarization vector p is just p z hat. So the direction of the electric field is negative p, negative or opposite the direction of the polarization. So you do the same for the electric field outside. And what do you expect to happen? You'll actually get the electric field of a dipole, but it's now in terms of polarization. So if you will recall, the electric field of a dipole is something like P over dipole moment P over 4 pi epsilon naught r cubed 2 cosine theta r hat plus sine theta hat. But P, the dipole moment, is actually just the polarization times the volume. In this case, the volume is 4/3 pi r cubed. So if you do that, it's so P here, the magnitude of the dipole moment is just the magnitude of the polarization times the volume, which is 4/3 pi capital R cubed. So what you will get when you get the negative gradient of the potential outside is something like this. You will have P R cubed over 3 epsilon naught R cubed. Then 2 cosine theta r hat plus sine theta hat. And you can actually write this in terms of the coordinate-free form. So in terms of the coordinate-free form, you can write this as r cubed over 3 epsilon naught r cubed, you will have 3 p dot r hat minus p. So similar with the electric field of a dipole, you can also write it in coordinate free form, free from any coordinate system. Okay, so outside it's a dipole. So if we try to draw our sphere now, this is our polarized sphere. This is the direction of the polarization. The electric field direction is actually like that. It's opposite the direction of the polarization. That's the electric field inside. And the electric field outside is the electric field of a dipole. So since there are positive charges here and there are negative charges there, so the electric field of the dipole is something like this. So near the sphere, the electric field outside is the electric field of the dipole, but far from the sphere, the electric field will approach to actually to 0. Okay, so this is what a uniformly polarized, the field of a uniformly polarized sphere looks like. So the electric field opposite the polarization, the electric field inside, and the electric field outside is that of a dipole. So to summarize this problem, this is the potential inside. So I can actually also write the potential as P dot R. Since P R cosine theta, this is just the definition of that product, of the dot product between P and R. So this is the electric field inside. So you can actually get this by taking the negative gradient of this potential. This is the potential actually outside. And I can actually get the electric field outside by taking the negative gradient of this. Sorry. So this is the electric field outside in spherical coordinates. This is the in coordinate free form. So example 3. So here is another look at a polarized sphere. So this is now what happens now if you have a uniformly polarized sphere. There are positive charges, bound charges on the upper surface. There will be negative bound charges on the lower surface. There will be no charges at the equator because cosine theta there is 0. We can actually treat the polarized sphere as two overlapping spheres of charge. So if we do that, so something like this, you have a uniformly charged positive sphere and you superimpose it, overlap it with a uniformly charged negative sphere. So in the overlap region, the positive and negative charges will cancel each other out, so 0 charges. So only in the upper region will there be positive charges, and in the lower region there will be negative charges, essentially mimicking our polarized sphere. So we can actually treat the polarized sphere as two overlapping spheres of charge. Okay, sorry. So of course, you will still get the same results. So this is just another solution to this problem. So essentially, the electric field inside is just the polarization, negative of the polarization, so opposite the direction of P. And for the electric field outside, it's the potential of or electric field of a dipole. In terms, but it's now described in terms of the polarization P. So this is another way of looking at a polarized sphere. So I will leave this to you. Okay, for the last example, what if you have a uniformly polarized cylinder? So the much easier way to do this is, again, similar with example number 3. You treat this as two cylinders, uh, two overlapping cylinders. One is a cylinder of positive charges, composed of positive charges, and the other one is a cylinder with composed of negative charges. So you do that. I will leave that to you. The method is actually just similar to example number 3, and you will get this result. Actually, the result is quite similar to what you have in the sphere. So this looks like a two-dimensional version of the result in example number 3. In example number 3, you have P over 3 epsilon naught, but here you have P over 2 epsilon naught. So it's just because it's a circle, it's circular, so two-dimensional sphere. So in the sphere, you have R cube over capital R cube over small r cube. But here, our radius is S, and still the total radius is R. So R squared over S squared. And it's 2 epsilon naught instead of 3 epsilon naught. And instead of 3 P dot R hat, you have 2 P dot S hat minus P. So the result is actually quite symmetric for cylindrical, for this uniformly polarized cylinder. So you can imagine a uniformly polarized cylinder as a two-dimensional version of a polarized sphere. Okay, so I will leave this example to you. So that's the end of the lesson on polarization on dielectrics. So in the next lesson, we will be discussing about a new quantity in electrostatics called electric displacement. So I will see you again in the next lesson.